I want to talk about climate change and the impacts on extreme events, and I want to start with some of the basic data about climate change before I then move to the actual impacts that the ongoing global warming has on weather extremes. So let me start with some very basic look back into history. I want to remind people that already Alexander von Humboldt wrote that man changes climate by cutting forests and by emitting large amounts of steam and gas at the centers of industry. So this is not a very new concept. Of course, Humboldt in 1843 didn't know yet what the gases were that caused the greenhouse effect. The greenhouse effect was already known since Fourier, 1824, but the question which gases cause it was only answered by John Tyndall in 1859, who demonstrated in laboratory experiments that it's water vapor, carbon dioxide, and a number of other gases which absorb in the infrared and thereby hinder the outgoing long-wave radiation. And he already wrote down this very nice description of the greenhouse effect. He said, the atmosphere admits of the entrance of solar heat, but checks its exit, and the result is a tendency to accumulate heat at the surface of the planet. So it's an excellent description because Tyndall demonstrated in his laboratory experiments that the shortwave radiation that comes from the sun is let through by the atmosphere. We all know the atmosphere is transparent to that because you can see the sun in the sky. But the atmosphere is not transparent at the infrared radiation level, where we try to get rid of the heat again into space. And that is why these data are of some concern, because one of the prime greenhouse gases, carbon dioxide, has been increasing dramatically in the last 100 years due to our emissions. We know this increase is entirely caused by our emissions because we simply know how much fossil fuel we dug up from the ground and burned, so we know how much CO2 was emitted by human activities, and what we emitted amounts actually to about twice as much as what we see here in the atmosphere as an increase. So it's not like there is some natural source for that CO2 increase, but the opposite is true. The natural Earth system has actually absorbed about half of the extra CO2 that we have taken out of the Earth crust in form of carbon and fossil fuels and then emitted to the atmosphere. So I was just trying to tell you, first of all, here's a global mean temperature evolution since the year 1880 from the NASA data. And we were just talking about these year-to-year natural variations where you get some colder years. Pinatubo, you can see that's about 0.1 degree below the average line. And some warm years, the biggest kind of spike to the warm end was this big El Nino event in 1998, which was the biggest El Nino that was ever registered. And more recently, we've had a couple of colder La Nina years. And as I mentioned, if you now forget about most of the time series and kind of cherry pick a short section, it looks like there's no warming here in the last 10 years. But that really is an illusion that simply comes from that year-to-year natural variability. And in fact, we have independent time series that describe this natural variability, like El Nino events or volcanic eruptions or solar cycle, which is an irregular 11-year cycle. And you can correlate these variability factors with the global temperature and subtract them out, just like the unemployment statistics are corrected for seasonal effects, for example. It's a very standard technique. And what you then end up with is this blue curve. The gray curve shows the original data. In this case, it's the average over all 5 global temperature time series that we have. And you can see here this warm El Nino year, 1998. And if you do this simple statistical correlation technique and subtract the effects of El Nino and La Nina, then you kind of get rid of that warm spike and it comes down here. You get rid of the cold Pinatubo effect and you get rid of those 2 cold La Nina years. And if you do that, you see that the remaining underlying trend after correction for the short-term variation, is completely steady warming trend, and there is no indication of any slowdown in this warming. You can also look at, just from the data perspective, how that is connected to the possible driving factors. Although, as I said, really the whole thing is based on physics and not on some data correlation. But if you insist on looking just at the data correlation, then here you have the global average temperature curve, again in gray. You have the CO2 curve in blue, and the scaling between the CO2 curve and the temperature curve here is chosen just as it should be, namely just so as the IPCC predicts, and it's predicted on the basis of that climate sensitivity that I showed you earlier. You have to be aware that some clever people will, first of all, they will not only show you just the last bit here, but they will also then add a CO2 curve that is grossly out of scale relative to the temperature curve, so that it looks like CO2 has increased dramatically while temperature was flat. That is just a kind of deception, I would call it. Now, if you look at the solar activity, which in the media again and again, we just had this in Germany a couple of weeks ago, again, the solar activity is blamed for all kinds of things. But if you look at the actual data for solar activity, it just basically shows the very well-known 11-year Schwabe cycle, but no trend. And so it certainly can't explain this warming here. And it doesn't explain very much anyhow, because the amplitude is so small. This amplitude here, how I show the solar activity, is the amplitude that you get when you actually do the proper statistical correlation analysis between the solar data and the global temperature. Then that is the imprint that the solar activity has on global temperature. It's only of the order of plus minus 0.05 degrees. And just as an illustration of that fact is that the warmest year on record, 2010, coincides with the end of the deepest and longest solar minimum that we have in the observational record in the last 50 years here. So this is a very new paper that came out about 2 weeks ago, which was the first reconstruction of global mean temperature for the entire Holocene. So this goes back about 11,000 years, and that's the blue curve. And what it shows is that temperature throughout the Holocene has this kind of funny bump shape, which is not surprising if you know what the main driver of natural climate variations in the last tens of thousands and hundreds of thousands of years was, namely the orbital cycles, the so-called Milankovitch cycles, which actually when I was in school, I learned about the Milankovitch cycles and causing the ice ages, etc. And that was in the early 1970s, that was established science and school stuff in the geography lessons in Germany. And the dominant cycle here, the Milankovitch cycle, is the precession cycle, which has a period of 23,000 years. And so you see the second half of that cycle. And so it's like the second half of a sinusoidal curve. And we're coming out of the ice age just here. And then we have this Milankovitch forcing, which leads to a slow cooling trend in the last several thousand years, which is the underlying reason why stuff is coming out of under the glaciers now that was buried there like 5,000 or 6,000 years ago. If you think of the Ötzi in the Alps, for example, he disappeared under the ice somewhere around here, and he's coming out now because temperature now recently is for the first time in a long time exceeding again that level in the early Holocene. And another paper that just appeared in Science about the Calcaya ice cap in the tropical Andes shows also that the ice cap has shrunk now to a size that it had 6,000 years ago, which is again is quite consistent with this overall global temperature evolution. And if you add to that what we expect now in this century, which is, depending on the emission scenario, could be 3-4 degrees warming or even more, then you can see that we are kind of way outside anything experienced in the Holocene. And also that implies way outside anything experienced in the last 100,000 years, because before that you have 90,000 years of ice age, where it definitely was a lot colder than in the Holocene. So we are really, at the moment here, we are exceeding the temperature level that has ever been experienced in the last 100,000 years. And you can see that from the melting glaciers. This is just an example from New Zealand. You can see it from the shrinking polar ice cap here. This is the sea ice on the Arctic Ocean. This is last year, and that's what it looked like in the 70s. So we've lost almost half of the ice cover in summer on the Arctic Ocean in the last decades. And if you look at the time series here, that's the ice extent on the Arctic Ocean from the observations, and you see this very steep decline, which is by some colleagues is called the death spiral of the Arctic sea ice. And you can also see, if you compare it with, this is IPCC report 2007, and models have improved now. They show somewhat kind of lower amount of ice, but they still get overtaken by the actual observations. So the IPCC estimates of sea ice decline were too conservative. Now, if we look into the future depends on us, because we have become by far the dominant factor affecting the global radiation balance and therefore the global temperature. And so it depends on the emission scenario. As climate scientists, we don't predict emissions. That's not our job and our expertise. And also I'm firmly of the belief that the future in terms of human actions, emissions, is not something to be predicted, but it's rather something that we can shape. And so we just have to look at what the options are that are in front of us to make informed decisions of which future do we actually want. And these are two examples of a rather high and a rather low emission scenario. And of course, there is a lot of scenarios in between as well that get evaluated. But kind of the optimistic case, this is very successful climate policy. We managed to keep warming below that famous 2-degree level. But if we don't, but that requires the emissions to go down quite rapidly here. In this blue scenario, you see the emissions. Now, if we continue on this path of ever-growing emissions that we are on now, then we will end up with, this amount of global warming could be by the end of the century. So 2100 is here, anything between 4 and 7 degrees thereabouts, but then continuing afterwards beyond that. And that would be a completely different planet. At the height of the last ice age, the global temperature was only between 4 and 7 degrees colder than now. And so if we're adding now another 4 to 7 degrees, we will really change this planet completely. That was just a look at the global average of the temperature. I was going to show you a movie which is not on this computer now, so this is the one thing that you lose by us switching computers, but the movie would show that the warming is not uniform, but the continents warm more than the oceans. If you have a global average warming of about 4 degrees, then most of the continental areas will warm by 6 degrees or more. And that's very important because we live on the continents and we grow our food there. And the second factor is that you have some hotspots of warming where the snow and ice cover shrinks, especially in the Arctic, but also in the Himalayas you get this effect. So you get less reflection of solar energy back into space because you have less bright surfaces of snow and ice. And in these areas, like in the Arctic, you can then expect a warming of 10, 12 or more degrees. So global warming is not uniform, and those global average numbers are deceptively low because most of the globe is covered by ocean, which warms relatively less than the land areas where we live. Now, the final point before I come to the extreme events is the sea level rise. It's also something we need to understand, extreme events, especially storm surges. Sea level is rising. This is the observational data. And it has risen by about 20 centimeters in global average since the year 1880 with significant local variations. And you can also see that it has accelerated this rise. You can see this by eye really. If you can compare it to the straight linear trend line, you can see that in the late 19th, early 20th century, we had a smaller rise of the order of 1 millimeter per year. But at the end here in the last 20 years, we have a rise that is about 3 millimeters per year. And this rise, as far as we can reconstruct it from sediment core data, for example, is unprecedented for at least 2,000 years. Here you have a reconstruction, the best that we have so far, that was published in 2011. The blue curve here is the reconstruction based on some sediment cores on the US East Coast. And it shows that sea level was relatively flat for most of the last 2,000 years. There was some sea level rise here associated with a medieval warm period between about 1000 and 1400 AD. Then sea level stagnated again or even slightly dropped in the so-called Little Ice Age. And then it started really with an accelerated rise that continues until today. And for the future is highly uncertain in terms of sea level. It's much more uncertain than the temperature future, because the physics of sea level rise is complicated. There are several contributing factors: the thermal expansion of the ocean waters, the melting of mountain glaciers, and there are thousands of mountain glaciers, and the melting of the big ice sheets in Greenland and Antarctica. All of these things are quite difficult to calculate, much more difficult than global temperature. And so we have a wide uncertainty range here. This is a factor of 10. This is the latest global sea level projections available from NOAA in the United States for the National US Climate Assessment that is currently being prepared. And the rise estimates range between the plausible lowest value of 20 centimeters to a plausible highest value of 2 meters by the year 2100, with a kind of more likely range between half a meter and a bit over a meter here. And that's also what I would say is a kind of a likely range of rise. The lowest range would actually mean that sea level rise would have to slow down compared to those 3 millimeters per year that we had in the last 20 years, because if that simply just continued unchanged, it would already give you 30 centimeters in a century. And I think everything argues for the sea level rise accelerating further rather than slowing down. So now I finally come to the extreme events. And there was a nice overview published by the World Meteorological Organization in 2011 in this brochure, where the key statement is that the decade 2001 to 2010 was the warmest ever recorded, and it was also marked by numerous weather and climate extremes that were unique in strength and impact. So there were many unprecedented extreme events in that decade, and we have examined that in a paper ourselves that was published last year, just a year ago, where we look at the connection between these unprecedented extreme events and the overall global warming from different perspectives, from the point of view of physical reasoning, from the point of view of statistics, and from the point of view of modeling. And we just compiled a list of some examples of extreme events that are particularly well documented in the scientific literature. So we know from long, reliable time series that they are unprecedented for a century or more, etc. And they are put on a map here. The fact that they cluster here in Europe has nothing to do with the fact that Europe has actually experienced more unprecedented extreme events, but simply because we selected ones that are very well documented in the scientific literature, and that happens to be in Europe and the United States because we have the strongest science base there. And this was actually then taken up in the famous World Bank report that was published at the end of last year, where they also included a list that was based on our paper. And I want to, you don't have to read this list now, I will give you a few examples of what I mean by these unprecedented extreme events. And let's start with heat waves. Summer 2003 was, many of you might remember that, it was called the summer of the century, at least in the German media, and also especially in France and Switzerland. You can see the maximum heat here was over France. And this kind of heat wave is not harmless. It caused about 70,000 additional fatalities in Europe, so it's really one of the greatest natural disasters that we have experienced. Now, it was actually, if you look at the average over the whole of Europe, including Russia, it was the warmest. 2003 was not the warmest. It was beaten again in 2010. This is the distribution of European summer temperatures. To the right, you see the warm years. To the left, you see the colder years. And you can nicely fit, if you look at this histogram, it nicely fits a bell-shaped curve, the Gaussian normal distribution. But you can also see that the recent summers have really marched outside of that normal bell-shaped distribution. And the warmest summers in Europe since the year 1500 have been 2010, 2003, 2002, 2006, and 2007, which clearly shows you that, this is not just some random distribution. There's something systematic going on here. And of course, with every single event there, the media call us up and say, is this global warming? And then every time we have to explain, well, a single event, you can't draw any real conclusions from a single event. But if you look at the overall picture here, you clearly see there is a systematic change in response to warming here and not just some freak weather. And of course, you can do this analysis globally, which we've done in a paper that was just published very recently, where we looked at 150,000 time series around the globe for every calendar month since the year 1880 and looked at how often in the last 10 years you get an unprecedented heat record in one of these time series. And we plotted this here on a global map as a factor by which that is increased over what you get in an unchanging climate. In a stationary, unchanging climate, heat records would just simply happen by chance, and you can calculate how many you expect by chance in such a 130-year time series, and then you can compare it with what you actually find, and this is the factor by which that is increased. So in global average, the factor is actually 5. So in global mean, we find 5 times as many monthly heat extremes as you would expect in an unchanging climate. So this is a perhaps to many surprisingly large effect that this less than 1 degree global warming has already had, that we have 5 times as many record hot months now than you have in an unchanging climate. And there are some hotspots like here in parts of Africa where you get up to 20 times as many record hot months in the last 10 years than you would have expected in an unchanging climate. And you can look at this as a time series as well rather than a map. And you see that the number of heat records here in the thin orange line is highly variable from year to year. This is this famous El Nino year again, 1998, which already in the global average temperature, it stands out. And in the number of monthly heat records, it really stands out. It's very high. But if you smooth that, you get this thick red line to get rid of the very large year-to-year variations in the number of records. And you can see you get an overall increase up to about this number of 5 that I mentioned. Roughly now we're at about 5 times as many records as expected in an unchanging climate. And the blue curve is from a very simple stochastic model where we simply assume we have this global warming trend, we have random noise, and how many records do we expect? The simple assumption that you can make. And you can see that the overall long-term trend is in the observations is conforming to what you would expect from that very simple statistical exercise. So in that sense, once you have thought this through, it is not surprising that you got 5 times as many records, because once you do the simple statistics, that's exactly what you expect from that global warming trend. There's another way of looking at heat extremes, and that is a paper that was published by Jim Hansen from NASA and some colleagues, where they looked at their global temperature data and they defined according to how many standard deviations above the average temperature a particular month or actually season, summer season here was. They defined that as either hot or very hot or extremely hot. I think the extremely hot was 3 standard deviations or more above the average, and very hot is 2 standard deviations, and hot is 1 standard deviation. And You can see the underlying distributions here from 1951 to 1980. You have this nice Gaussian, and you have the hot ones in red and the cold ones in blue. And you have practically, you don't see any extremely hot ones. Now here you have 1981 to 1991, 1991 to 2001, and then finally the last decade. And you can see how that probability distribution shifts towards the right to ever warmer temperatures, and how this occurrence of the very hot and extremely hot, the extremely hot is I think the dark red here, how that has really increased greatly. You find none of that here, but now in the last decade you find a significant fraction of these extremely hot regions at any given time. And so here is the percentage of the area of the globe that is covered by the different temperature categories. And so initially you have about 30% or 33% hot and very little very hot and extremely hot, but the very hot part has increased to about 30% by the last few years, and even the extremely hot that you didn't have between 1950 and 1980 is now covering about 10 or even in this peak here up to 20% of the globe. And so at any given single location, when you're struck by an extreme heat wave, you might think, well, you know, this is freak weather. But if you look at this, you see that now permanently about 10% of the globe is covered by this extremely hot weather, and then you realize it's not some freak event. It's a very systematic trend that comes from global warming. Now, the temperature story is quite simple, and any layperson will understand. If the global temperature increases, then the number of heat extremes increases, and you can quantify that as I have done. But much more tricky is the changes in precipitation, because it's not clear if the temperature gets hotter, does the precipitation increase or decrease? And it turns out that it does both. In some regions it increases, in others it decreases, and it also changes its distribution over the year between the seasons, and also the partitioning between kind of your average long-lasting rainfall and some extreme rainfall events. You actually tend to get more of the extreme events. But here just shown is the observations of the annual average rainfall, and you see in Europe, southern Europe gets less and less rain. This is the observed trend, whereas there's some hint that Scandinavia might get more rain. This is the model result for the prediction for a greenhouse gas scenario, where you see pretty similar picture. The models predict consistently actually a drying out of the Mediterranean and more precipitation over Scandinavia. Now the consequence of that drying out of the Mediterranean is increasing drought problems in that area, which then lead, for example, to these fire problems that here we see in August 2007, which were huge forest fires that almost burned down the antique site, the historic site of Olympia. That was just prevented in the last minute, luckily. But this has become quite a normal picture on our news, that we have big fires in the Mediterranean area in summer, which is, of course, then people say, okay, the fires were set by some people, etc., which is all true. But the fact that these get increasingly out of control has to do with that long-term drying out of the Mediterranean region. We don't only have this in the Mediterranean. There are some other parts of the globe that suffer from increasing fire risk. Australian bushfires, February 2009, another example of these unprecedented events where a lot of lives were lost. And the reason for these very bad fires is that it was an unprecedented heat wave that exceeded anything in the recorded history of Australian temperatures. And this is just an example of one of the newspaper headlines from that tragic event. Now, the flip side of drought is extreme rainfall events, and there is indeed some physics, first of all, that would make you expect that a warmer climate overall produces more rainfall, because the whole water cycle is enhanced. You get more evaporation from the oceans, and therefore what goes up must come down. You get more rainfall. But you also have a tendency to get more extreme rainfall events. That has a different reason. Because warmer air can hold more moisture, and if you have a given weather situation where you have the atmosphere loaded with moisture and that then all rains down because the air hits a mountain range or something like that, which is a similar thing that happened with this Elbe flooding in 2002. In a warmer climate, you simply get more rainfall out of that same saturated atmosphere, because for every degree warming, you can put 7% more moisture in the atmosphere before it reaches the saturation level. That's basic physics, Clausius-Clapeyron equation, which determines how the saturation vapor pressure depends on the temperature. And so here you have the Elbe flooding, one of the most damaging extreme weather events in Germany. And you have similar problems in other parts of Europe. 2007 had extreme flooding in Britain, and it was May to July was by far the wettest in England and Wales since record keeping began in 1766. So it's another of these unprecedented extreme weather events which caused a lot of damage here, estimated financial damage, £3 billion. You probably remember this Pakistan flooding event, which coincided with the Russian heat wave, and there indeed might be a physical connection that operates through planetary waves. And this was the worst flooding in history, and again, it was caused by rainfall records. So this is for us, if we want to put it down to climate change, you have to separate out whether there are maybe some changes in the river catchment that were made, etc., which of course can contribute and probably did contribute to the Elbe flooding as well. But the primary reason for the Elbe flooding and this Pakistan flooding was that amounts of rainfall fell that had never been recorded in the history of measurements before. And this flooded area then was actually the largest freshwater lake on the planet while it lasted. Here's a satellite view of that Pakistan flooding. And the World Meteorological Organization, which is produced quite an unusually clear statement for a UN organization, I thought, when they said this was an unprecedented sequence of extreme weather events, and this type of event matches the IPCC projections of more frequent and more intense weather events due to global warming. Here's an interesting extreme rainfall example from Australia, 2011. And because the rainfall is water that has evaporated from the oceans before, and Australia is an island, you can try and look at the sea surface temperatures around the Australian region. And this is a picture here for the November sea surface temperature anomaly in the Australian region. And this massive rainfall record happened in a year where the sea surface temperature recorded an all-time high. Here you see an overall warming trend in the sea surface temperatures around Australia, and this was a particularly extreme year with very high sea surface temperatures, which is one of the reasons why you then get these excessive rainfall amounts. As a curiosity, this rainfall extreme caused an exceptional blip in global sea level. Global sea level went down. It has now recovered, it's back up again, but it went down for I think almost a year or so, because all this rainfall here was soaked up by the soil in Australia, and that water was missing from the oceans, and it was so much that you could actually see it in the satellite measured global average sea level. So now I come to the final type of extremes, namely storms. And storms are even more tricky and uncertain issue than rainfall extremes. I mean, I kind of moved from what is pretty simple physics and quite well understood, namely heat extremes, to kind of less well understood and more complex issue, namely drought and precipitation. And now the probably physically most complicated thing to understand and predict and measure is storms. But there is some indication that globally the strongest cyclones, now talking about tropical cyclones, are increasing, at least since we have good data. That's the satellite era that started in the late 1970s. Before that, there is a lot of dispute about the data quality about storms. but since the arrival of the satellite, we have a homogeneous data record, and it shows here, as on this axis, how strong a storm is. On the right-hand side is the strongest storms, and on the left-hand side, the weaker tropical storms, and the trend on the vertical axis. And you can see for the weak storms on the left half of the diagram, there's no significant trend. Here's the 0 line. But for the strongest storms, those are the most damaging ones, category 4 and 5 tropical cyclones, you see a clear, statistically significant trend in increase. So the strongest storms are getting stronger, and there is some physical reason behind that, because the energy that these storms, that drives these storms, comes from the warm oceans, warm ocean temperatures. That's why they occur only in the tropics. And if the ocean temperatures get warmer, you might expect that the very strongest storms, that are those that otherwise have ideal conditions. They don't hit land before they get too strong, or they're not destroyed by shear winds. If everything else is right and you have ideal conditions for a storm to fully develop, that it can fully develop to an even stronger storm if you give it even warmer sea surface temperatures as an energy supply. And that's borne out by the observational data. And we had, in 2004, we had a kind of completely off the scale, unprecedented hurricane season in the Atlantic, where we had 28 tropical storms, and the previous record was 21. 15 reached hurricane strength, previous record was only 12, and 4 reached the maximum category 5 hurricane strength, and the previous record was only 2. So this is really, in all kinds of measures, unprecedented event, and Hurricane Wilma was the strongest ever recorded in the North Atlantic, and we also for the first time recorded a hurricane in the South Atlantic. Now, Kerry Emanuel's a kind of prime hurricane expert from the United States, has produced these statistics that show the hurricane power, which is an integrated measure over the duration and wind speed of these storms, how that has evolved since the 1950s. And the blue curve shows the sea surface temperature in the tropical Atlantic. And you can see there is quite a good connection between the two, although more recently, in the recent few years, the hurricane power is kind of lower than what you would expect from that correlation. And there is discussion of whether maybe some of that increase here was caused not just by warming of the surface, but by also cooling in higher up in the atmosphere, the stratosphere. There's still unresolved issues there, but overall it looks like with a general warming trend, you may be getting more hurricane power. And the global average temperature curve is here shown in this dotted line, just to show you that there is nothing very special happening in the tropical Atlantic in terms of temperatures. They're basically similar, show a similar increase as the global mean temperature here. Now, I want to finish up with New York, which is a particularly vulnerable large city. And there's a study published in 2001 by Cynthia Rosenzweig, who analyzed the storm surge risk for New York City. This is a map of Manhattan here, by the way, in case you haven't recognized it, the lower part of Manhattan. And in that study, they basically predicted everything that happened during Hurricane Sandy, all the impacts that such a storm would have. And they also showed that what is now a once-in-a-100-year flooding event, that is what is shown here with this blue. That's how far the water penetrates into the street grid of Manhattan. This is a once-in-a-100-year event today, based on past statistics. If you have a 1 meter higher sea level, you get this kind of event once in every 3 years, even if the wind statistics are unchanged, simply because you start from a higher sea level, so you need less of a storm to reach that level of flooding. And so that's one of the very simple and basic consequences of sea level rise, that you have a massively increased storm surge risk and frequency. And as my talk progresses, it gets more and more speculative, and now I'm kind of coming to the most speculative part, namely Hurricane Sandy. This is not so speculative. As I said, the sea level rise made the storm surge worse. That's obvious. Now, this question, warm SST tends to sustain and strengthen a storm. That is certainly true, but there are other factors as well. Maybe not necessarily going to be the dominant effect. Some of the damage of hurricanes comes from the extreme rainfall event that goes with these events, or snowfall in this case partly. And there, everything else being the same, if you have a warmer ocean, you get more evaporation and therefore you get stronger precipitation event. But the most speculative scientific discussion that is going on now is whether the funny track that Hurricane Sandy took, the fact that it actually turned left and hit New York, whether that has anything to do with climate change. And there are some intriguing hints in this direction from a number of studies. Here are 4 different studies that show a connection between the loss of sea ice in the Arctic and changing weather patterns in the northern hemisphere mid-latitudes. Especially, they show that if you remove sea ice in the Arctic, you get a tendency to form a high pressure area here. These are surface pressure maps centered on the North Pole here. Here's Greenland. And this red blotch is a high pressure that you get if you, in model simulations, if you remove some sea ice in the Arctic. This is a similar pattern. You get high pressure over the Arctic area, but this is not from a model. This is a data analysis for the last decades, where they correlate sea ice extent and pressure in the Arctic. A similar study here by Francis and Vavros, where they compared pressure patterns in different time periods and find that more recently, with the strong Arctic warming, you get more high pressure here, especially here again over Greenland. This is a piece over Greenland. And here's a study by Liu et al., which comes to a similar conclusion. I should have rotated this. This picture is 90 degrees rotated compared to the other ones for some reason. So here's Greenland, but you see between Greenland and Iceland here, you see anomalous high pressure as a response again to sea ice loss, as they show in their model simulations. And now if you compare to what happened with Sandy, this is a track of Sandy, and usually the hurricanes kind of continue off into the North Atlantic here, but Sandy made a funny left turn here. And the reason was that near Greenland here there was sitting a high pressure area which blocked the further progress of Sandy. And yeah, as I said, there is some indication that this kind of high pressure situation in the northern Atlantic might be made more common, more frequent due to the Arctic warming and sea ice loss up there. So, as I said, that's quite speculative. With that, I want to end. Here's a little advertisement if you want to read one of my books. And if there's German speakers, because there is teachers here, this is a book for children from roughly the age of 10, which won the Environmental Book Prize of the Year last year in Germany, which actually some of the illustrations in my talk were taken from this book, from the illustrator Klaus Ensikert, who is my favorite children's book illustrator. Thank you.